So in some sense, you can talk about the delay of a gate when placed in a circuit, okay, and thereby you can also talk about the delay of a you can talk about the delay of that gate in that particular circuit, right, given the capacitances, the driving it that it is driving, and so on. Okay, so now if I take this particular circuit, okay, let me just take a that simple XOR gate. Okay, let's take that. Let's take the XOR gate that we had seen earlier, and okay, and now I want to ask, what is the time that the output Y will take for it to stabilize to the right value? Okay, I have an input A, I have an other input B, and I want to just find out what is the delay. Okay, so now what you see is, first of all, one of the inputs, right? So there are 4 NAND gates, N1, N2, N3 and N4. Okay, so there are 4 NAND gates here, and each of them have inputs coming from different levels of logic. Okay, for example, N2, one of the inputs is coming from the output of N1, whereas the other input is directly coming from what is known as the primary input. Okay, this is called the primary input. Likewise, this is called the primary output. Okay, which means they are basically the interface to the macro or the circuit, right? So now let us assume, okay, I am going to mark the delay. Two things. First, I will make a very simplified assumption: rise time, fall time, they are both the same. Okay, it doesn't really matter even if the numbers are slightly different. So let's assume that rise and fall doesn't matter, right? And then I'm also going to make certain other assumptions that I'll come to a little later, right? I'm also going to assume that the delay from one input to the output is the same irrespective of which input I'm talking about, though in reality it need not be the same. So from A to Y or B to Y, it doesn't matter, okay? So I will just write a delay number here, okay, which basically is, I'll say, sorry, let me say 100 picoseconds, okay, and for N2 and N3 I am going to say the delay is 75 picoseconds, okay, and this one I'll assume that it's driving a large capacitance which I have not shown here, but the delay could be 400 picoseconds, okay. So first of all, as I mentioned repeatedly through this lecture, the delay of the same NAND gate, remember it's the same NAND gate that I have placed in 4 different locations, okay, it's the same NAND 2 gate, right, but they can experience different delays, right. Okay, so now what does this mean, right? So if a change occurs in input A, right, it will take 100 picoseconds for that change to go through to the output of that NAND gate, right. So therefore here, so let me just show you this example. Let me tie the input B to 1, okay, I am going to tie B to 1, and then I am going to now plot the output. So let me just label these nodes, okay, X, right, this is U and this is V. I'll also write them in different colors so that, sorry, so that I can U, right, and then in V. Yeah, okay. So I have A, B, X, U, V and Y, okay, and I will plot Y in maybe green, okay. This is what I am going to do, right. So let us consider this example where I have the four gates as with delays shown here, and I am now going to ask at what point will the output Y stabilize to its actual value, right? Given that the input A makes a transition at a certain time, right, at t equal to 0, after how long will it take for the output Y to stabilize to its final value, okay? So this is what we are going to call as static timing STA, static timing analysis. Okay, we will not worry about the exact exact definition and meaning. We'll just get an intuitive feel for what happens to the delays in a circuit. So when A actually makes a transition at t equal to 0, right, the output X of N1 will stabilize to its final value at 100 picoseconds, right. So therefore in blue I will just write what is known as the arrival time of X. What is the arrival time? It is basically the time after which you can measure the output and be sure that the output is correct, okay. So if you wait at least 100 picoseconds, right, after input A makes a transition, right, that means we are assuming that the input A arrived at t equal to 0, okay. So let me write that in bracket here, okay. This arrived at 0, X will arrive and stabilize to its final value at 100. Now N2 sees two inputs, A and X. Obviously X is coming later and therefore the output U should react only to X, right. It may react to A also, but again if I ask what is the arrival time at U, right, let me write that definition. Arrival time, the I'll say minimum time at which we can sample the and be sure the output would be correct actually, right. So if you look at this NAND gate, right, what are we saying? So if A is making a transition here like this, you cannot sample it before t fall because otherwise you will get a wrong value, right. So in some sense we are saying you got to sample it at least after the arrival time, okay, and be sure that, so if I for example if I sample the output here, I know the output will be 0, right, but if I sample it much before, right, I know the output might not stabilize to its final value and therefore that's an issue, okay. That's why we are saying what is the minimum time at which we can sample the signal to be sure the output would be correct, okay. That is what we are talking of arrival time. So now the arrival time at U, now because of the input A making a transition, you could have a transition at U, okay, but is that the final value? No, because the other input is making a transition only after 100 picoseconds, and therefore this arrival time at u is going to be the max of arrival time at its input plus its delay. Okay, so I will write this as max of 0, 100 plus its delay. Likewise for v, right, this guy, it is max of again 0, 100, okay, because b also is sort of ready at t equal to 0, right, plus its delay 90 picoseconds, okay, and therefore the arrival time for u is equal to 175, for v equal to 190. Now N4 is the final gate. You have two signals, one arriving at 175 picosecond and other arriving at 190 picosecond, and therefore the final arrival time is going to be again max of 175, 190 plus 400. This is equal to 590 picoseconds. So what this means is that after 590 picoseconds, you are guaranteed that the output y will stabilize to its final value. Okay, and this delay can sometimes be prohibitively large if the implementation of that gate is not good. Okay, so let us consider one example here. Okay, and the process of, by the way, of propagating these arrival times through that circuit is what we call static timing analysis, right? Essentially we find the arrival time. So the arrival time, okay, here arrival time at the output is equal to max of arrival time at inputs of the gate plus its delay. Okay, this is how arrival time is defined for a gate, and you just keep doing this and then find out what the final arrival time is. Okay, so let us consider two different implementations of an AND-N logic. AND-N logic. Okay, what is the AND-N logic? We had discussed one of this earlier, right? I have A0, A1, and then I have progressively adding another input by cascading the output of the previous AND gate, right? A0, A1, A2, A3, okay, and let me do one more, okay, A4, okay. This is one implementation of a AND phi gate. Okay, I'm going to talk specifically of an AND phi logic. Okay, I will talk about another implementation, AND 5 logic, implementation 1 and implementation 2. Okay, so I have y here, y equal to A0, A1, A2, A3, A4. Okay, now what I'm going to do, I'm going to do the following: A0, A1, okay, then I'll do A2, A3, and then A4. Okay, this is an alternate implementation that I'm going to look at. So if I look at this, I'm going to do the following: A0, A1, right? Then I'm going to do second gate like this, A2, A3, okay, and right, finally I will do A4. Y. Right? So clearly this tells us, that this, these gates, these two implementations are identical in terms of functionality, right? Both implement the same AND phi logic. Okay, and let's also look at this. Each AND gate is driving only one other AND gate. So if you look at, let me label them N1, N2, N3 and N4, right? Here I'll call them M1, M2, M3 and M4. So I have really not even simplified or reduced the number of gates. Okay, let us just look at this. Now I can assign delays. Okay, let me say that the delay for each of these gates is 100 picoseconds. Okay, right? Every gate, because they are all, you know, uh, driving only one other gate, right? A copy of itself, right? So I can assume that they all have the same delay. Now let us go ahead and actually plot the arrival times. Okay, I am going to write the arrival times on each wire, okay, in magenta. These are all primary inputs. You can assume they arrive at time equal to t equal to 0, right, without loss of generality. Now output of N1 will stabilize max of the arrival time of N1, the inputs of N1, that is 0, 0 plus 100. So this will stabilize at 100, right? Now for N2, two inputs, one is a primary input which comes at 0, the other input comes at 100, so the max is 100. So 100 plus 100, 200, right? Likewise for N3 it is 300 and N4 it is 400. Okay, now just look at the corresponding implementation on the right hand side. I will write the arrival times in blue. Okay, A1, A0 and A1 all arrive at 0, A2, A3 they are all 0, right? And the two, and therefore the output of M1 will stabilize after 100. Output of M2 will also stabilize after 100. Okay. Now M3 sees two inputs which are arriving at 100 and 100, and then there is a delay of 100. So this will stabilize after a delay of 200, right? Now M4 is seeing two inputs. One is a primary input, because there is an asymmetry in the number of inputs, right? We have 5 inputs. It's not a power of 2 and all that. A4 arrives at 0. The other input arrives at 200, and therefore this will arrive, the output will stabilize at max of 200, 0, which is 200 plus its own delay, which is 300, right? Clearly you see that this implementation, right, implementation 2 has lesser delay. Literally by 100 picoseconds, right? That's why this idea, and imagine now if I just continue to, had continued to do this for a 10 input gate or a 12 input gate or so and so on, right? You can already see that if I group these gates together in bunches of 2, it is much better than propagating the output of one, cascading the output of one to the input of the other, right, as shown on the implementation in the left. Okay, so that's the reason sometimes you also need to be aware of the delay of these gates, because logically they might be the same, but in terms of delay they might be very, very inferior, right? So I urge the viewers to sort of work out, right, what happens if I tried this for a AND 10 logic, okay, AND 16 logic. Okay, let's keep it as powers of 2. You will see that if you go ahead and do it in a nice, sort of a very nice grouping in sets of 2, right? The implementation will come out very nicely with very little delay, right? It's also interesting to note that the logic depth right here is on the left hand side is 4. 1, 2, 3, 4. Whereas on the right hand side the logic depth is just 1, 2, 3, right? And therefore that actually contributes significantly to the delay of a circuit, right? So let's keep this concept, though it's a slightly abstract concept at this time because we do not know about the transistor level implementation of logic gates. Let's keep this model in mind because it will help us understand certain other circuits from a delay perspective very well. So I'll stop here, and then in the next lecture we will move to what is known as hierarchical implementation of circuits. Thank you.